Hello, everyone. Today, I'm going to present two state-of-the-art approaches that utilize graph neural networks in the field of computer vision. The first paper is titled Vision GNN, an image is worth graph uploads, which demonstrates how graph neural networks can revolutionize the way we represent images in visual tasks. The second paper is Layout GMN neural graph matching for structure layout similarity, focusing on structure layout comparison in designs such as floor plans and user interfaces. We will explore these two papers separately, going deep into their methodology, experiments, and key contributions. Graph neural networks are a class of neural networks specially designed to work with graph structure data. In graphs, nodes represent entities and edges represent the relationships between them. Unlike traditional convolutional neural networks, which assume data is arranged in regular grid-like structures, graph neural networks can efficiently process data that is irregular or contains complex relationships. This makes them particularly useful in visual tasks where objects and their paths may not fit neatly into grid-like structures. The power of graph neural networks lies in their ability to capture both local and global dependencies, enabling models to understand the context of each entity and its surroundings more efficiently. The first paper we will look at is Vision GNN, an image is worth graph of loads. The main innovation here is to move away from the traditional grid-based approaches used by convolutional neural networks and instead treat images as graphs. In this model, patches of an image are represented as loads, and their relationships, such as spatial proximity or content-based similarity, are represented as edges. This approach is particularly effective when dealing with irregular objects, where traditional grid-based models may fail to capture important contextual information between different parts of the image. The flexibility of a graph representation allows Vision GNN to process visual data in a more natural and efficient way. Vision GNN was motivated by the limitation of existing models like CNNs and transformers, which treat images as either grids or sequences. As shown in this figure, the image data is usually represented as a regular grid of pixels in the Euclidean space. Convolutional neural networks apply sliding window on the image and introduce the shift invariance and locality. The recent vision transformer, or MLP, treats the image as a sequence of patches. For example, VIT divides a 224 times 224 image into a number of 16 times 16 patches and forms a sequence with length of 196 as the input. Vision GNN addresses these limitations by representing the image as a graph, where the structure is much more flexible. It can model complex relationships between different parts of the image, making it especially powerful for tasks involving objects that don't fit neatly into regular patterns. In Vision GNN, images are divided into patches, with each patch representing a node in the graph. These nodes are collected by edges that are determined by their spatial or context-based relationships. For instance, patches that are close together in the image or share similar visual content will be collected in the graph. This graph structure enables the model to capture not just local relationships between neighboring patches, but also global relationships across the image. This is a significant advantage over convolutional neural networks, where the receptive field is limited and the relationships between distant parts of the image are harder to capture. The core of vision GNN is a grapher model, which performs a graph convolution. In this module, each node representing a patch of the image updates its representation by aggregating information from its neighboring nodes. This allows the model to capture context, for example, how different parts of an object relate to each other. The graph convolution is designed to handle this aggregation efficiently, ensuring that information flows between nodes. Importantly, this helps the model understand both local structure, like the texture or color of a patch, and global structures, such as the overall shape of the object. More technically, graph convolution in the graph module works as follows. Each node I in the graph aggregates information from its neighboring node J using a aggregation function G. This function combines the features of the labels and updates the node's representation accordingly. Mathematically, this can be expressed as this formulation. Here, G is the aggregation function that combines the features of node J, and H is the update function for node I. This allows the model to propagate information across the graph, helping each node learn from the context of its labels. As a result, the model captures both the fine details and the global structure of the object. The authors further introduce multi-head update operation of graph convolution. In this approach, each node aggregates information from multiple subspaces known as heads. This allows the model to capture diverse features from different perspectives, making the learned representations more robust and better suited for complex visual tasks. This multi-head approach is similar to the attention mechanism used in transformers, where multi-heads allow the model to focus on different aspects of the input data. To avoid the problem of over-smoothing, where the features of overloads start to become indistinguishable after several layers of graph convolution, Vision GN incorporates a feed-forward neural network module. This module applies nonlinear transformation to the node features, ensuring that nodes retain their unique characteristics even after they aggregate information from their labels. Oversmoothing is a common issue in deep graph neural networks, where nodes become too similar to each other. But FFN helps prevent this by introducing additional complexity and nonlinearity in the feature space. Vision GNN is implemented using two architecture variants, isotropic and pyramid. In the isotropic architecture, all layers maintain the same number of nodes and feature dimensions. Similar to transformer networks, this ensures a uniform treatment of features across the entire model. On the other hand, the pyramid architecture reduces the feature size as the model goes deeper, focusing more on high-level features in the later layers. This is akin to convolution convolutional neural networks, such as ResNet. In ResNet, the spatial resolution decreases and the receptive field increases in deeper layers. The pyramid structure is particularly useful in tasks like object detection, where multi-scale feature representation is important. There are two examples. The left figure shows the isotropic architecture, and the right figure shows the pyramid architecture. Vision graph neural network comes in three variants: tiny, small, and base. These variants offer different trade-offs between performance and computational complexity. The tiny one is the smallest and most efficient model, designed for scenarios where computational resources are limited. The small one makes a balance between performance and efficiency, while the base one is the largest model, providing the best performance at the cost of higher computational requirements. This flexibility allows Vision GNN to be applied in a wide range of tasks, from lightweight applications like mobile devices to more resource-intensive tasks, such as large-scale image classification. Vision GNN was evaluated on several standard benchmarks on the ImageNet classification task. Both isotropic and pyramid Vision GNN achieved good performance on top 1 accuracy, which is highly competitive with state-of-the-art models. This performance outperforms that of traditional models like ResNet and Swing Transformer, which are well established in the field of image classification. What's particularly impressive is that Vision GNN achieves this performance while maintaining a similar computational cost, making it both accurate and efficient. This makes Vision GNN an attractive option for large-scale image classification tasks, where accuracy and efficiency are equally important. The authors conduct an application study of the proposed method on the image classification task and use the isotropic model as the base architecture. They test the representative variance of graph convolution. From table 6, we can see that the top 1 accuracies of different graph convolutions are better than that of detail. Among them, max relative achieves the best trade-off between flops and accuracy. From table 7, we can see that directly utilizing graph convolution for image classification performs poorly. Adding more feature transformation by introducing FC and FFN consistently increase the accuracy. In addition to image classification tasks, Vision GNN excels in object detection tasks, where the goal is to locate objects in an image and classify them. The graph-based representation is particularly effective for detecting irregular shaped objects, as it allows the model to capture the relationships between different parts of the object. For example, in a real-world scenario, an object may be partially occluded or have an unusual shape, but Vision GNN's ability to model these relationships in the graph helps it accurately detect and classify the object. The superior results in this table demonstrate the generalization ability of Vision GNN architecture. This figure shows the graphs of two samples in different depths. The pentagram is the center node, and the nodes with the same color are its labels. Two center nodes are visualized as joined. All the edges will be messy. We can observe that the proposed model can select the contact-related nodes as the fourth-order labels. In the shallow layer, the label nodes tend to be selected based on low level and local features, such as color and texture. In the deep layer, the labels of the center nodes are more thematic and belong to the same category. The VIG network can gradually link the nodes by its content and semantic representation and help to better recognize. Now let's move to the second paper, layout GMN neural graph matching for structure layout similarity. This paper presents a method specifically designed for comparing two-dimensional layouts, such as floor plan or user interface design. In many design applications, the goal is layouts that are structurally similar, even if they differ in appearance or minor details. One of the key challenges in comparing two-dimensional layouts is that traditional methods such as intersection over union are inadequate. This method measures the pixel level overlap between two layouts, but it doesn't capture the structural relationships between elements. Layout GMN leverages the power of graph neural networks to learn these structural similarities by representing layouts as graphs and matching them based on their structural features. This allows for more accurate and efficient comparison than traditional pixel-based methods. As shown in this figure, layout GMN learns a structural layout similarity metric between floor plans and other two-dimensional layouts through attention-based neural graph matching. The learned attention width, the number shown in these boxes, can be used to match the structural elements. For example, the 099, the 091, they show the similarity of the two parts of the layouts. Layout GMN represents each layout as a directed graph, where the nodes correspond to individual elements in the layout. For example, rooms in a floor plan or buttons in a UI. The edges represent the spatial relationships between these elements, such as their relative positions or distances from each other. This graph-based representation allows the model to capture not only geometric relationships, such as the size and shape of the elements, but also thematic relationships, like which rooms are adjacent to each other or how UI components are aligned. As shown in this figure, given an input floor plan image with rooms segmentations in A, we abstract each room into a bounding box, and obtain layout features from the constituent semantic elements as shown in B. These features form the initial node and edge features of the corresponding layout graph shown in C. The nodes in layout GMN and characterized by both geometric and semantic information. For example, a node representing a room in a floor plan would include features such as the size and position of the room, as well as its semantic label, such as bedroom and kitchen. The edges between those capture the special relationships, such as the distance between two rooms or their relative orientation. These features are essential for understanding how the layout is structured and how different elements relate to one another. The core of layout GMN is an attention-based graph matching network, which compares the graph representations of two layouts. The model performs message passing both within each graph and across the graph being compared. Message passing allows the model to propagate information between the nodes, learning how different parts of one layout correspond to parts of another. The attention mechanism helps the model focus on the most important part of the layout, weighting the relationships that contribute the most to structural similarity. This process ensures that the model learns not just which layouts look similar, but which ones are structurally equivalent. The attention mechanism in layout GMN plays a crucial role in identifying which parts of one layout correspond to parts of another. By assigning attention weights to different parts of the graph, the model is able to focus on the most important relationships between elements. For example, in a floor plan, the attention mechanism might focus on the adjacency of rooms or the location of doors, which are key features in determining structural similarity. This allows the model to align layouts based on their online structure, rather than just their pixel-level appearance. Layout GMN is trained using a triplet network architecture, which consists of anchor positive negative pairs. The anchor is a layout that the model is currently trying to classify. The positive is a layout that is structurally similar to the anchor. And the negative is a layout that is different from the anchor. During training, the model learns to minimize the L2 distances between the anchor and the positive layouts, while maximizing the L2 distances between the anchor and the negative layouts. This is done using a triplet loss function, which encourages the model to group structurally similar layouts closer together in the learned embedding space. Layout GMN is trained using weakly supervised learning, where AOU-based thresholding is used to generate labels. Intersection over union is a simple pixel-based metric that is used to distinguish between positive and negative examples during training. However, while IOU provides a rough measure of similarity, the goal of layout GMN is to go beyond IOU and focus on structural similarity. By learning from these weak labels, the model gradually improves its ability to compare layouts based on their structure rather than just their visual overlap. One of the primary applications of layout GMN is layout retrieval. In this task, the model is given a query layout and asked to retrieve structurally similar layouts from a dataset. Layout GMN consistently outperforms other methods, such as IOU and GCN in terms of retrieval precision, meaning that it is better at finding layouts that are truly similar in structure. This makes it an invaluable tool in fields like architecture design or user interface design, where finding structurally similar layouts is essential for optimizing workflows and creating consistent design. The performance of layout GMN is evaluated using two key metrics: the precision K-scores and overlap K-scores. Precision K-scores measure how many of the top K retrieval layouts are relevant, while overlap K-scores measure the consistency of the retrievals. In both cases, layout GMN significantly outperforms traditional methods, demonstrating its superior ability to consistently retrieve layouts that are structurally similar to the query. These results highlight the model's effectiveness in layout retrieval tests, where precision and consistency are critical. Here are some qualitative examples of layouts retrieved by layout GMN. In these examples, the retrieved layouts are structurally similar to the query, even though they may look different in terms of pixel arrangement. For example, there will be some minor differences between the pixel arrangement, but it has low influence on the similarity to the two layouts. The model focuses on relationships between the elements. For example, how rooms are collected or buttons are arranged in a user interface, rather than just their appearance. This makes layout GMN particularly useful for designing tasks where structure is more important than visual similarity. Another key application of layout GMN is label transfer. Given a labeled layout, for example, in this figure, as shown in this figure, there are source and target. There are two layouts. One is source and the other is target. And we want to transfer the label of the source layout to the target layout. Given a labeled layout, the model can transfer those labels to a structurally similar but unlabeled layout. This is particularly useful in tasks such as user interface design, where designers often reuse the same components across multiple interfaces. By automatically transferring labels from one layout to another, layout GMN can significantly speed up the design process and ensure consistency across different designs. One of the major advantages of layout GMN is its ability to capture structure similarity more accurately than traditional methods, such as IOU, because it focuses on the relationships between elements. It is much more robust to noise data or small misalignments, which are common in real-world applications. This makes layout GMN more reliable in tasks such as layout retrieval, label transfer, and design optimization, where consistency and accuracy are critical. In fact, the layout GMN offered us a new metric and a new method to metric how the similarity of two graph layouts, and is particularly significant. In conclusion, both Vision, graph neural network, and layout GMN represent significant advances in their respective fields. Vision graph neural networks provide a flexible and efficient solution for general visual tests, achieving good performance in image classification and object detection. On the other hand, Layout 解门 specializes in structure layout comparison, offering a powerful tool for tasks such as layout retrieval and label transfer. All in all, this method showcases the versatility and potential of graph neural networks in computer vision. Yeah. And we believe that graph neural network has more potential that need to be further investigated in the future. That's all. Thank you for your attention.